All right, 4.3, derivatives of inverse trig functions. And I do have your quiz graded, so I'll give it to you after we're done. All right, so basically these, I mean, as you probably saw, like they're kind of weird derivatives. It's like, where in the world does that even come from? But essentially we're doing that, but a lot of them end up being a chain rule as well, because it's not just like, you know, the derivative of the inverse sine of x. So they end up with a level of the chain rule to them. Overall, these aren't like a huge part of the AP exams, so we don't spend a ton of time with them. We're going to spend a little bit of time with them, but not anything too crazy with this section. So we'll just jump in. Find the derivative of y with respect to the appropriate variable. So number 4, we've got y equals the inverse sine, or arc sine, whatever, of 1 minus t. So when we do this, we treat the stuff that's inside just like it was x, and then we're just going to take the derivative of that inside piece after the fact as part of our chain rule. So the first thing I would do, I would have y prime is equal to, well, inverse sine is 1 over the square root of 1 minus, and then whatever x is anything that's in this parentheses in here. So this would be 1 minus t all squared. And then outside times the derivative of the inside, which would just be -1 in this case. So then I just need to simplify anything that's in here as much as possible. And so I would end up with -1 over the square root of 1 minus, and then this would be a perfect square trinomial, so 1 minus, 2t plus t squared. And then I just need to essentially fix the signs on these with this negative. So I'll end up with 1 minus 1, so that part just going away. So I've got -1 over the square root of 2t minus t squared once I simplify it. And that's just the derivative of that. So it's not super hard. It's just, these are just very odd.
Where'd the 1 go?
1 minus 1.
Oh.
I just did, like, as I went. I just did the whole thing.
Okay.
Yeah, so this is, a lot of times this, well, I don't want to say a lot of times, but it happens a lot that ends up going away. So, but yeah, then you can just leave it like that. Obviously, I mean, if there's something that you can factor out, we should, but a lot of times they just get left like this, and it's kind of like, it's kind of annoying, but it is what it is. All right, 8. We've got y equals 1 over the inverse sine of 2x. So, have we done anything with u substitution yet? Like, where like we decided what u was, or did we only do it where they gave you u? Okay. So, first of all, I would probably rewrite this as the inverse sine of 2x all raised to the -1. Otherwise, I'm doing a quotient rule, which can just get really confusing when we have the inverse trig derivatives that are all fractions anyways, because then you end up with fractions and fractions, and it's just kind of a lot happening. So kind of a couple ways that we can go about doing this. We can just try to treat it purely as a, you know, it's going to end up basically being a double chain rule. Or I can use u substitution. So I'm going to do it with u substitution just so that you can see what that would look like. But essentially, I need to choose something to be u. And since I have a double chain rule, I'm going to actually use this whole inner piece to be u. So I'm going to say let u equal the inverse sine of 2x. So then the derivative of that part would be du dx, or u prime, however you want to write it. would then be 1 over, find the inverse trig derivatives. I'm awful at remembering what they are off the top of my head until I use them enough for a little while. So this would be then 1 over the square root of 1 minus, in this case it's 2x, and then that 2x is squared, times the derivative of the inside, which is 2, so times 2. So that ends up just being 2 over the square root of 1 minus 4x squared when I square the bottom part and simplify it. So now what I can do is I can go back to this over here and I can say, okay, well, y equals u to the negative 1. And I'm going to take the derivative of that, and then anywhere there's a u, I'm going to replace it with my whatever my u value was. So I would end up with the derivative would be negative u to the negative 2 times du. So this is like what we did with the implicit, so this is where that kind of comes in. We'll actually do a lot more with u substitution in the future, but for right now, this is kind of where we're at. But because I'm technically taking the derivative of y with respect to x, then when I replace it with u, I've got to take the derivative of u with respect to x. So that's where this is coming from. So this is really times, I guess I should say, du dx here, which is where this is going to come into play. Or if you write it as u prime, that would be it. So then now I can go and I can replace u with the inverse sine of 2x, and then I can replace du with this derivative here, with what I found. So then I end up with, I guess I should write y prime here. So y prime is equal to negative, and then in parentheses, the inverse sine of 2x all to the negative 2, and then times 2 over the square root of 1 minus 4x squared. So that's the two pieces there.
Do I have to do it this way?
No.
Okay.
If you can see it as just a normal chain rule, I'm mainly just showing you this way so that you can see what like an intro to u substitution, because there's going to be problems later on that it's going to be way easier to do this method with. Okay. But we'll get more into that, because it'll be stuff where like I'll be asking you, okay, what should you be in this situation? Like, what should we choose to be? And it'll be easier. I just like giving you like a little intro to that. Okay. But you'll get the same answer either way if you do it just as like knowing that's a double chain rule. So then I need to move this to the bottom. I'm going to leave the 2 on top. So I end up with negative 2 over the inverse sine of 2x, and that whole piece there is squared. And then I'm going to put the square root of 1 minus 4x squared then on the bottom as well. And so that's my final answer with it like that. But yeah, I go back and forth on if I was doing this like purely just for me, if I would do u substitution, or if I would just try to do the double chain rule. I would say most of the time I probably would just do the double chain rule, but I just like to show that. So that's the only one I'm going to do that way. I'm going to do the other ones just normal. Anyways, any questions on that one since that was a lot? Okay. All right, the next one so we're back to, if you remember, our particle moving and all of that. The next ones are back to that stuff. So a particle moves along the x-axis so that its position at any time t greater than or equal to 0 is given by x of t. Find the velocity and indicated value of t. So essentially we're going to take the derivative and then plug in the value to find what it was. So 12, I've got x of t, so my position function is the inverse tangent of t squared, and t is equal to 1. Now, the inverse tangent, inverse cotangent are my favorite ones because there's no square root in them, so that's nice when we do that. So the derivative, I've still got a chain rule here because I've got this inside, obviously. So my v of t for the derivative is going to be 1 over 1 plus whatever's inside. So this is going to be t squared squared. And then times the derivative of what's in the parentheses, so times 2t. So that ends up giving me 2t over 1 plus t to the 4th. So that's the velocity function, and then evaluated at t equals 1. So I'm going to do v of 1 is 2 times 1 over 1 plus 1 to the 4th. So that just ends up being 2 over 2, which ends up just being 1. So not anything too crazy on those ones. My least favorite ones are secant and cosecant because they're just a lot more involved than everything else. But this will be another one of those things where I can pretty much guarantee a question on the quiz is going to tell you to write the 6 inverse trig derivatives. And then I'll check them for you so that you know that you've got them right. Obviously, you do need to be familiar with them, but I wouldn't stress over them a whole lot because it's not going to be that many questions on the exam at the end, if that makes sense. So, all right, find the derivative of y with respect to the appropriate variable. So we're just literally back to the same thing we were just doing previously. 14, y equals the inverse secant of 5s. I don't know why they didn't put that in parentheses, but I'm going to put it in parentheses because it needs to be. All right, so this derivative is kind of one of the crazy ones. Now, did I have in your examples, did I put the variable, the x that's outside in absolute values?
No.
Okay, so technically speaking, well, let me look. Hold on. Where did it go? Arc secant. So technically, there's stuff about that the value that's outside needs to technically be the absolute value of x, so what's outside of the square root. But most of the time that number's positive, which is why we just kind of leave it off. So just to be aware of that, the number that's just in front of the, not that the whole function has to be positive, just that number needs to be positive. In this case, it's going to be because it's a 5s, but, so here we've got y prime is equal to 1 over, and then again, we treat this 5s as our x value. Also, if you don't like using s because it looks so similar to a 5, like, I don't care if you change the variables to x if you want to. Do you want me to, or are you going to? Okay. Some people are like, the s is like too much like 5s, and I'm like, well, I'm sorry. So anyways, okay, so we'd have 5s, and then the square root of 5s squared, and then minus 1. And then ultimately, I also have a chain rule, so the derivative of the inside would just be 5. So I'm going to end up with 5 over 5s times all of this, so the 5s are going to cancel. So if you want to go ahead and start with that, or like do that, then we only have to rewrite it once. So then y prime is equal to 1 over s times the square root of 25s squared minus 1. And then that's all we have to do on that one. Trying to hit some of these different ones here. Let's see. We haven't done cotangent yet. Let's do 18. So 18, we've got y equals the cotangent, inverse cotangent. I keep wanting to say cotangent to the negative 1. And then the square root of t, or the inverse cotangent of the square root of t. There we go. So if it's helpful, like we've been doing in other problems, we can rewrite this as the inverse cotangent of t to the 1/2, just so that we can see that chain rule happening, but up to you. So cotangent, another relatively easy one overall. I've got, this one is negative, so -1/, and then it's 1 plus the stuff inside, so t to the 1/2. But that is then squared. And then times the derivative of the inside would be 1/2 t to the -1/2. So then just to simplify this, I've got on top, I've just got the -1/2, or well, let me do this. The t to the 1/2 squared, that's just going to become t. So let me do this. Let me rewrite this as 1 plus t. And then this is technically all being multiplied by this. So I'm going to have 2 times this stuff in parentheses, or you can go ahead and multiply it through if you want to. The book leaves it separated, but either way is fine. So we'll have 2 times 1 plus t, and then this t to the -1/2 moves to the bottom. So you can either write it as t to the 1/2, or if you want to rewrite it as the square root of t like that, that would be your final answer.
Where did the 2 come from?
From the 1/2. So since this is also like a fraction, because this piece right here would be 1/2 times the square root of t.
Oh, okay.
Technically, is what that becomes. And then this
this
is
way.
-1/1 plus t, technically.
Okay.
And then these two things are being multiplied. So I just multiplied their numerators and denominators. I just kind of did it in one huge step instead of splitting it. What is this problem? Find an equation for the tangent to the graph of y at the indicated point. These ones are going to, there's really no way for you to do this problem in the sense of how it's set up, aside from you using your calculator. So again, probably not overly likely to be an AP question, but I want you to see one just in case. But this will be our last thingy here. So 24, we've got y equals the inverse tangent of x squared, and x is equal to 1. So obviously first thing I got to find the derivative, evaluate it at the point to get my slope. So y prime equals 1/1 plus x squared squared. If you want to go ahead and write it as x to the 4th, obviously feel free to do that. And then times 2x, the derivative of the inside. So this ends up being 2x over 1 plus x to the 4th. A lot of times when I'm evaluating, depending on what it's actually asking me for, like if it says find the derivative, like, and show what the derivative is and then evaluate it, then a lot of times I'll do this separate, but I'll do this at x is equal to 1, then that just says I'm evaluating it at that. So then I would have 2 times 1 over 1 plus 1 to the 4th, so that ends up just being 1, which is my slope. Now, they only gave me the x value, so to find my y value, obviously, I need to plug in here for inverse tangent. The catch here is when you do this, you've got to do it as a radian mode.
Okay.
So pretty much everything that we do is always going to be radian mode in calculus unless it specifically says otherwise, because it's going to end up giving you a weird answer. So to find y, we would have to do the inverse tangent of, well, basically 1 squared. Now, you, technically speaking, if you know enough about your inverse, if you remember your inverse trig functions and the rules about where they exist, you could technically do this without your calculator, because tangent occurs on the right side from minus pi over 2 to pi over 2, and you're looking for where the value is 1. So you could do this for all intents and purposes without it. Look, I'm in degree mode. Now, if we get back to physics where we're doing stuff, you're going to have to watch because your calculator could end up in the wrong mode, and that obviously is super annoying. So the inverse tangent of 1, I get 0.785. So my point then is at 1 and 0.785. Now, if you remembered that occurs at pi over 4, because that's where tangent is 1, that would be how you would do it without the calculator. Some of them are not that easy to do without your calculator, though this one just happens to be one that's a known value, but some of them aren't. However, your calculator is using the the book is using the decimal value when they write your equation of your line. And then you just do it like normal. So y minus 0.785 is equal to 1 times x minus 1. And then, as you usually do, you can leave it there or we can move it over. So y equals x minus 1 plus 0.785, which ends up giving us y equals x minus 0.215 for my tangent. So only a few problems with this section. 1, 5, 11, 13, 15, 19, and 25. I think I've tried to kind of hit like one of each of the inverse trig derivatives so that you can use it, but I don't know for sure if that quite gets them all.